Sí, perfecto. Bueno, bienvenidos, gracias por venir. Ya me pronosticaba una lluvia bastante fuerte, pero todo bien. Bienvenidos, hoy tenemos a James Zimmer de la Universidad de Pardee, bueno, de la Escuela de Pardee, de graduados. Nos va a estar presentando sobre Identifying Legislative Communities of Interest Using Contact Graphs. Y creo que va a estar bastante interesante. Espero la disfruten. Va a ser en inglés, pero bueno, lo avisamos varias veces, pero no tenga ningún tema. Y también nada más recordarles, todos los meses, al final de mes, probablemente todos los jueves, seguimos aquí en la casa, en nuestra casa, que es el TEC, la Escuela de Gobierno. Y también los interesados, acabamos de abrir un Patreon, sobre todo para que si alguno quiere también apoyar, vamos a estar dando calcomanías, camisetas, algunas entradas para los eventos como el AI de la TAM. Ya tenemos también algunas entradas gratis para poder ir al evento. Y sobre todo los próximos que vayan a entrar, vamos a tratar de estar consiguiendo, y sobre todo las dinámicas que siempre hemos hecho para regalar esas entradas, y también pues para pagarle aquí a nuestro buen streamer un sueldo decente y que pueda vivir de esto. Entonces, muchas gracias por venir, espero lo disfruten. Adelante.
All right. Well, I got loud really quick. Yeah, thank you for having me. I'm sorry, I'm not really at the level where I could conduct this in Spanish. I would like to try, but I think that would be pretty brutal. So, one, I want to thank DataPub for inviting me and having me here. I'm really honored to be able to talk to everyone and share this work. This is ongoing work as part of my dissertation. Yeah, and so if anybody's not totally familiar with, I'll give a really quick high-level overview. In the United States, every 10 years, we go through redistricting. We just underwent the 2020 census. And so last year in 2021, amid COVID and everything, we redrew all our legislative districts. And those districts are what we use to actually elect representatives to the national and state legislatures. So with all that being said, I'll just dive in. The title of it, Identifying Legislative Communities of Interest Using Contact Graphs. And I'll go through some definitions here so that we're not all totally lost. Really high level, the general idea here is that preserving communities may be good for representative democracy. This is an open question. There's a lot of theoretical evidence to kind of support this, but empirical evidence is kind of light. So there are challenges in actually there's kind of challenges to answering this question empirically and in practice to actually preserving communities. There's a whole bunch of different layers. So many communities go overlooked in the redistricting process. There's a lot of selection bias on who actually is able to communicate with whoever draws our boundaries in government. There's a lot of there's a lot of conflicting information, and on top of that, there are communities that don't get represented, and through all of this, whoever's drawing the legislative districts, they're also trying to work through a flood of a ton of information. So, if anyone's not familiar with this, this image over on the left here has anybody seen this image before? Maybe it's a very U.S.-centric image. Okay, it comes from the late 18th century, and this is the origin of the term gerrymander. So this was a district. This is an image from the Boston Gazette. I think it's 1798, and what it's showing is a district kind of snaking around the entirety of the state. You can't see the head on the right, but it kind of has this really odd shape. And the governor at the time was Governor Elbridge Gerry. And this was called Elbridge Gerry's salamander, and that's where the term gerrymander comes from. So the reason I put this here is because the high-level motivation for all of this work, in the United States, we have single-member districts, and we have a set of kind of criteria for how we draw these districts that makes gerrymandering, it enables gerrymandering, and it enables to do this in a really nefarious way. So the real motivation behind this is reducing this practice of gerrymandering. And I realize I didn't define gerrymandering. So gerrymandering is this idea of drawing legislative districts in a way that preserves or enhances political power. We often think of it in terms of partisan gerrymandering, but there's things like incumbent protection gerrymandering, there's things like racial gerrymandering, all kinds of ways that you can cut and slice these districts to give certain groups political power over others. So one of the examples in the US that's pretty common is thinking about like North Carolina or Ohio. Those are prominent examples where Republicans, for example, have, even though, you know, maybe they comprise 48% of the state, they've got 75, 80% of the legislature. So this is kind of, this is one big overarching motivation. So let me give a really quick kind of nested diagram here. I don't know if anybody's totally familiar with US federalism, but it's not that different as far as I know from Mexican federalism. So there's the national government. Within that, we have states, which kind of are independent governments. And then within those, the state is responsible for drawing congressional districts. And so those are the representatives that will send to the U.S. House of Representatives. And then the state legislative districts. So that's, each state has its own legislature, and they're responsible for drawing those districts. So states have the responsibility to draw these districts. And so states have a lot of power over elections in the United States. And gerrymandering can occur at any level. So it can occur at the congressional level, it can occur at the state level. And the idea here is to consider whether or not, you know, communities of interest play into this. And let me kind of skip through a few things. I want to get to the meat and potatoes of the data science stuff. So every state has its own set of different criteria. I put New Mexico up here because that's where I'm from. But there's some federal criteria here. Every congressional district has to have equal population, follow the Voting Rights Act. And then at the state level, a lot of them have compactness, preservation of certain boundaries, and then this thing called communities of interest. So within this kind of, these space of criteria, you can draw a lot of different maps. The space is really, I mean, practically infinite. This is just an example of 3 potential maps that were, you know, considered for acceptance in 2021. And you can see there's a lot of variation between the kind of 3 maps. There's really big kind of differences in the districts. So all this being said, we want to answer questions about how preserving communities can actually improve the process of drawing these districts. So what is a community of interest? It's a really, really fuzzy concept. It's a criterion in 24 states in the United States, so there's no uniform definition. The California Constitution has a nice definition. It's a contiguous, like a geospatially contiguous population that shares common social and economic interests that should be included, I don't know why it says relatively, but within a single district for purposes of its effective and fair representation. The idea being you want to preserve groups that have similar interests together so that their interests can be represented in the legislature, so that when they elect someone, there's someone to respond to their concerns. One of the things gerrymandering does is it cuts communities up, or it puts too many communities in the same, you know, kind of the same basket, the same legislative district, which can dilute their vote power in aggregate. So this is an example of a community of interest from, I think, the 2000 redistricting in Los Angeles. This is just a submission that someone did, and it's an example of kind of the primary way in which these communities are identified. Usually advocacy groups, members of the community come together, they draw boundaries, and they submit it to whoever's doing redistricting. That could be a state legislature, that could be an independent commission, someone who's been given authority by the state to do it. So these are generally what they look like. It's just boundaries on a map, right? It's pretty simple conceptually once you see it. But the idea is they're pretty fuzzy. There's a lot of ways to argue for, you know, whether or not one or another might be a community. And one of the other issues with them is that there's this massive selection bias. So backing up to talk about the process a little bit, in California, every 10 years when we go through redistricting, the California Citizens Redistricting Commission is in charge of taking all this public feedback. I mean, 30,000, I think in 2020 they got almost 40,000 notes, maps, just whatever, people standing up and speaking at public meetings, 40,000 pieces of public information over the course of 11 months that they have to sort through and sift through to try to decide how to draw districts. This is an image that I took from a 2020 paper by Olivia Rambo. And it's a choropleth detailing kind of where public commentary and feedback comes from. So I'm going to come over here. Let me adjust my microphone. So the red areas are areas where there's a lot of feedback coming from. White means there's no public feedback. So for those of you who aren't familiar with Los Angeles, this is Malibu. It's a very, very wealthy white area. This is Burbank and Glendale and Pasadena. These are all fairly wealthy areas. Down here, there's San Pedro and some of the beach South Bay areas. In general, there's a strong bias here towards wealthy areas, whiter areas, and a lot of the central city where most of the people live, you're seeing no feedback coming in. So there's a huge selection bias on who's actually, have the time and resources to participate, to actually go to meetings, to submit feedback, who has the organizational capacity to submit this information. So that's one of the issues here. A lot of these communities are not getting any voice in the process. The other side of that is there are communities where there are strong resources or there's a lot of feedback, but on the map drawer side, there's a lot of conflicting information. So I put up here, this is from the 2020 redistricting in California, and these are 6 different maps delineating Boyle Heights. Boyle Heights is a historically Hispanic and Latino community on the just east of downtown Los Angeles. And there's a whole bunch, if anybody's familiar with Los Angeles, freeways are kind of like, that's how we define everything. Those are our landmarks. So it's a little hard to see on the screen, but you have this one, for example, it goes from, on the western boundary, this is like I-10, I-5, all the way to 710, and it's a pretty expansive, see these 2 lines? This is 10 and this is 60, so it covers that entire range. Down here, this is a different one. You'll see that this is the 5 and this is 10 and 60, but it doesn't make it cuts off right here. It's a line. There's a pretty expansive difference here, and I did some of the, like a really rough calculation, and the variance in population between them, there was like a difference like 30,000 people between kind of the minimal community and the maximal community. So there's a pretty big range of difference here between, on the conflicting information. So finally, the last motivational piece for this is to think about theoretical questions surrounding COIs. This is an example of a really, a gerrymander was struck down in 1995 by the Supreme Court. And this was actually a VRA, a Voting Rights Act district that was drawn. So in the United States, we make special, we try to draw these minority majority districts to make sure that minorities get representation. They struck this down, and this was a predominantly black district where the idea was to put a bunch of black constituents in the same place so they had some voting power. One of the things we don't really understand is to what degree, this is something called packing. We're putting a bunch of minorities in the same place. So one of the things we don't really understand is to what degree should you keep communities together versus split them apart. And there's not a lot of good empirical data to think about communities. There are some that really deal with, say, race and ethnicity. But think about communities as a whole. There's very little empirical data to actually answer these questions. So now that I've talked through all of this, we can actually model these COIs using some simplifying assumptions. So I'm just going to present them quickly. We're going to assume that COIs are geospatially contiguous. This is based on a lot of state definitions and generally what public submissions look like across states. Uniqueness. So the reason I say here single resolution is you might have communities that are relevant to different scales. So a community that's relevant to, say, a school board district, which might be, I don't know, a square mile or a few square miles, might be different than one that's relevant to a congressional district. So we have these different levels that we can think about. But at each level, we assume each person lives within one community. Completeness. Every resident of a state lives within a community with interest worthy of representation. This maximization of interest. So this is something that's going to get into our algorithm, the community detection algorithms that we apply. The idea is that communities of interest locally maximize some interest represented. So we don't know exactly what that is, but depending on the empirical data you select, it's going to group communities together or group people together in a way that maximizes their interest locally. And then the final piece is we are going to use some basic building blocks to construct these communities. And those building blocks there should be a reasonable basis to assume that they're worthy of being contained in a single community. So the idea, I put this on here, and I probably should have a more exciting picture than this one. So maybe I drop to this. The idea here is now we can, using these assumptions, we can model communities of interest as collections of tiles within a tessellation in a state. And so a tessellation is something like census block groups, census blocks in the United States. There is, and I'm forgetting the name of it, but there's an analog in Mexico. So using these, we can tile a state, turn it into a collection of block groups, and then this induces what we call a contact graph. So is everybody familiar with graphs and nodes and vertices and that kind of thing? Or, well, okay. So the idea here is a state is you have some geospatial extent of the state, right? And each one of these, you can turn that into a tessellation by just dividing it up, creating these geospatial tiles. And each tile is then associated with a vertex. So the vertex, we call it a contact graph because we draw an edge between two vertices if the tiles are adjacent. We define adjacency as them sharing a non-trivial border. And I point to this example because E and I, they meet at a point, but they are not, that's a trivial border. They're meeting at a single point. And the reason we do this is because we're going to cluster them together based on the graph. And we want to make sure that it's contiguous. So if I allow these two to be adjacent, theoretically they could be clustered and we'd have a discontiguous, technically not discontiguous, but practically discontiguous COI. So anyway, this is kind of the general idea. And then we can use empirical data about, socioeconomic similarity, community colocation to set edge weights. And then we can apply community detection. So I'll talk through, I have a more formal definition here. I wanted to just at least show the image on the right. This is an actual picture of what one of these graphs looks like. I'm going to talk through two data sets that we use to actually evaluate this method. So the first approach will be using traditional census data. Second approach, we will talk about cell phone and cellular device geolocation data and how we actually set that. But really quick, I just wanted to kind of show, this is outside of Atlanta. I just took a screenshot of a tool. You can see there's a lot of variation. The graphs get pretty dense or pretty big, pretty fast. But I think it's a cool image. There are these communities, the thicker edge weights here indicate stronger strength of connection between adjacent vertices. So there's some areas here, especially down here. I don't know Atlanta very well. I picked this because it looked good. So down here, there's kind of a cluster where we're seeing a lot of evidence of strength of connection between adjacent vertices. And then up here, there's some of that. Over here, there's some of that. Over here. But there's this overarching structure that kind of looks cool, at least. I'm going to skip past that. I don't think anybody wants to go through the really mathy on it. So just repeating here on the two methods and the approaches. So the first one is based more on how we traditionally think about, or how, I shouldn't say we, but how redistricting is kind of traditionally done with respect to identifying communities of interest. So a lot of the times they use census, race, and ethnicity, and then American Community Survey data, which it's a massive 5-year panel survey that the census does, and it keeps tracks of things like estimated income, education, language spoken at home, transportation, industry, tribal affiliations, all these really important components that we might care about for representation. One thing that's important to mention about all of these census data sets is all of those population counts and metrics are available and associated with their geospatial tessellations. So we have population counts by race and ethnicity at the block level, and the block level is super refined in the US. A block is quite literally a city block. So depending on where you're at, that can be, I don't know, it can be as few as 0 people in some areas, but if you're in a dense area like Los Angeles, it can range from 100 to 1,000 people. It just depends. And then those are in the ACS, since it's a survey and there's more statistical uncertainty, and they also want to, I think it's more, there's a lot more estimation going on. So they have things at the block group level, which is collections of blocks, and then the tract level, which is collections of block groups. Anyway, so the second one we're going to talk about is a more novel data set. I had the privilege of being put in touch with a group of volunteer data scientists with an organization called the Center for New Data, and they have all this cellular device geolocation data. So billions and billions of pings, right? For a bunch of I'm not going to try to say it, anonymized devices that they've got for 6 months or a year or something. They've got a bunch of data. So we said, why don't we see if you can use this to identify communities of interest? And this is a novel approach for a couple reasons. The data is super inaccessible. It's complex to work through. It requires teams of data engineers and scientists kind of helping to put the entire pipeline together. But I think it came out with some really interesting results, and it helps us think about, rather than just dimensions of similarity, what do natural communities look like if we assume communities are who you run into throughout the day? So let me skip through. I'll talk a little bit about how we do the similarity approach, and then maybe I'll show a couple results. And then I'll move on to the device geolocation data. So the first approach with similarity edge weighting is, now that we have these blocks and block groups that have different population counts associated for them, we could use a pretty simple way to measure the similarity between them. You have populations associated with different categories, right? Say within race, right there, I think there's 8 categories. There's white, black, Asian, some other race, 2 or more races, and Native American, I think, are the Native American alone. I think those are it. I may be forgetting one. Oh no, yeah, there's one more. There's Asian. There's Pacific Islanders. Is its own one. So anyway, we have these different categories by race, for example, and we can use this thing called cosine similarity to get a measure of how close or how similar those two. We use blocks or block groups. I'm going to just keep saying block groups, but you can scale it up or down. So we want to get a measure for how closely related those two block groups are. I'll show this because I just to explain this diagram a little bit. This is COI, and this might represent block group 1. This will block group J, right? And the two are adjacent. So we have a category C here. This might be race, and there's 12 people in category 1 here and 4 here. On J, there'd be 4 in the first category and 10 in the second category. And then when we look at the second, I'm using category poorly. When we look at the second dimension relevant to interest, such as language spoken at home, we might have different categories. And so we can kind of parse those out, 10, 3, 3, 1, 11, 2. And this is a little bit of an older image. There's a couple ways to do this. You can treat everything as a single vector like this, and then find the angle between it. the way the way I kind of move towards deciding is for each of these dimensions of interest, right? Race, ethnicity, language, income, whatever it might be. We calculate the cosine similarity between each of those independent dimensions, and then we weight the different similarities. And we can explore over those weights in kind of different ways. I put in a normalized similarity too. It's the same thing practically. But is this making some sense? Did I explain this well, what we're talking about? We've got some categorical populations, we've got an angle between them, and we can use that to set our edge weights. One other piece I'd like to mention that I'd like to add in one of the components that's relevant to interest, right, are political, maybe not our partisan preferences, but policy preferences. Like, what would we like to see passed? And it's hard to get at that in the US a little bit, but there are some imperfect measures. There are popular referendums that you can look at, and those are usually, there's vote tallies available by precinct. And precincts can be even smaller than blocks. They overlap, and it's different. They're not connected with the census precisely. But I would like to integrate proposition vote data. So you'll have in California, for example, we get to vote directly on amendments to the Constitution. This has positives and negatives. The negative part is most people, such as myself, do not have the time to really investigate every issue and make it's very difficult to know whether you're for or against something until you've spent like days reading about it. The positive side is that the Constitution can be directly responsive to the people if there's something interesting. So anyway, the reason this is interesting is it's nonpartisan, and you get a little bit better sense of like what people actually care about from a policy perspective. So this is a piece of data that I'm working on getting that I'd like to integrate into that. So I'm just going to show a couple. These are a couple different maps drawn using different scales of data, or I'm sorry, different scales of tessellations. So I'm pretty sure this is block group, this is block. So the left side here is what I'm calling kind of the trivial graph. And I actually have a tool that I'm going to show in a moment where we can actually look at the graph. So over here on the left side, this is, I talked about the edge weighting function, which I call phi, and this is 1. So if it's adjacent or not, we can still apply a community detection algorithm. And applying that creates this is kind of like, what does the topology of the network imply? And that's kind of what we're getting from this. It's done using block group level. And then if we go down to the block level, remember block groups are collections of blocks, we can create, there are these communities that are a little bit smoother and they end up looking a little bit different. Over here on the right, these are a little bit older, so I have a couple new images that I'll show as well. But over here on the right, these are constructed using PL94, which is like really refined block level data, but you can aggregate it to the block group. So there's data on race and ethnicity, and these are just run quickly using that information. You can see by comparing, this is no empirical data on similarity. This is empirical data on similarity. It's hard to compare them because if you might get different numbers of communities. It's really hard to say how to number communities and give them the same, because they're just going to be different. So I know that the visual comparison is a little difficult, but this is a nice little reference. Here it says Los Angeles. Here it says Los Angeles. So those are kind of decent centers. You can see like this over here and this over here are pretty different. This is where downtown Los Angeles is, and over here is kind of the heart of it. This is kind of where Boyle Heights is. So the communities look actually fairly similar, but I'll show some results that push those differently. In general, the idea is here, we're seeing different communities come up. Now, these haven't been calibrated to anything, and there's work that we're doing to do validation, to do calibration to available data. But in general, it's at least responsive. So these are a bunch of different COIs that were drawn using different dimensions in the data. or in like ACS5, and I zoomed in and tried to center on the Boyle Heights area. It's a little small. So, but anyways, we can see like up on the top, there's this one that's the top left is something called all. I just took like 11 different dimensions in the data. There's race, ethnicity, income, educational attainment, commute time, industry, language, means of transportation to work, sex, and veteran status, and age. So one thing that's kind of like, I have the sex on here, right? But that one's probably not going to be super informative most of the time. Because in general, the distribution of sex geospatially is relatively homogeneous. So we don't get a ton of information from that. But there are certainly areas where it is important. And like veteran status, for example, that tends to be fairly homogeneous till you find like communities of veterans that are in a certain place, and then it just pops out at you. The point of this graph is mostly to just show that there's differentiation that's coming out of this, and these are still under development, right, and still being validated. I tried to center on Boyle Heights again, but it's pretty difficult to see. So maybe I'll demo. There's a tool that we have, and I just want to kind of show it quickly. There's a tool for each of the data sets because we've kind of talked about them a little bit. Let me see if I can get my computer to. Okay, so I'm not an R shiny programmer, but tried to put this together. The idea here is I can explore through all these different demographic components, and when I say that, there's this all demographic communities, and this is one where I've used all of the different dimensions to set the edge weights. They're all weighted equally. I will talk a little bit later about how we're going to explore and make this more interesting. But then going down here, you can see there's the age-based communities, industry, sex, travel time to work. So those are communities where the edge weights are set solely on that dimension. So I have similarity scores for the different categories across that dimension, and that's the only dimension we're paying attention to. This is I can't see on my computer, so I'm looking here. So I have an example here of what a graph looks like. Let me go to this is West Los Angeles. Here's the ocean. This is overwhelmingly much wealthier than Los Angeles at large. Not quite Beverly Hills, but in general, if I click here, yeah, takes a minute to draw the graph on a shiny leaflet thing. So I think that the one I'm showing right now, this is language spoken at home. I had income up earlier. What am I missing? Household income. It's an H. Okay. So this is one that I spotted and I thought looked at least a little interesting. There's this gradient that happens. Like these ones seem to be really similar, and then for whatever reason down here they're not as similar, which is kind of interesting. You'll notice like a big dip here where these are a bunch of thin lines and nothing's really similar. That's because this is where the VA or the Veterans Administration Hospital is located. So either, I don't think anybody lives there. And if they do, it's probably people in situations who don't have a lot of income. Anyway, it's just kind of, you can see some of the differentiation showing up, and up here this is super wealthy, and so we kind of expect them to all be similar along this dimension. Let me see if maybe, I'm going to zoom over here. Let's see if I can find the Boyle Heights region. Yeah, so this is kind of the area around Boyle Heights that I've been talking about. Maybe I'll go I'm going to change it to a different community type. And okay, ethnicity. So one of the interesting things here about Boyle Heights in general is it's separated, so it's really, really similar along this ethnicity dimension. And these, I know this is kind of hard to see on here, and the coloring's not amazing. So I also include nodes outside the community, so you can kind of see what's adjacent to what. But these light yellow dots are kind of what this community of interest is. And it's pretty tightly bound network. All the lines are really thick, so everything's really similar in here. This is Montbello, and this is kind of the Boyle Heights and East LA area. And this whole area is predominantly Hispanic Latino. But there's one kind of key dimension that separates the two, and it's income. And it's at least, we at least see some kind of responsiveness here to the differentiation, where there is a cut in the middle. So while this isn't a perfect validation, it helps us. It's one level of validation. We're seeing responsiveness to like known differences between the communities and that kind of thing. Now, I would say these are not anything I would go to I'm not advocating for these as our final communities yet. There's a lot of work to be done before we get there. Yeah. So we have a similar tool for the cellular device geolocation data. And maybe what I'll do now is I'll back up and start talking about that process and what that data looks like, and then the next step following it. All right. Let's go back to the slideshow. Okay. Let's start from scratch. Okay. Sip of water. So the first question was how can we do this using socioeconomic similarity? And now the second one we're going to do is how can cellular device geolocation data be combined with these graphs to actually help us inform the structures of legislative communities of interest. So I have this slide in here. I think everyone should be a little bit more familiar. I'm not an expert on dwell clustering, but the idea is we start from we have raw device geolocation data. So there's billions of pings across millions of anonymous devices. I think over the course of a month in the United States, we have about 10% of the population. So the Center for New Data maintains these databases. They have partnerships with OutLogic and Veristat, and they will use some of the data to calculate these dwell clusters for different anonymized devices. So I was just kind of showing an example of how we take pings and transfer it to dwell clusters. But the idea is over time, you can follow anonymized devices, and then you see where they start pinging a lot in these, close geotemporal regions, right? So there's a high frequency of pings within a small space at a time. And this could be someone at home walking around, I don't know, playing with some app, right? You're on Farmville, and you've given them your geolocation data for some reason. And so it's keeping track of this. And now we have a whole bunch of dwell clusters for each device. So this is everybody here works in data science, I think, but for me, this was the creepy part of it, is now you can actually infer where a device lives, right? So looking at a dwell cluster with the, highest frequency of visiting a certain dwell cluster, you can start to tease out where these devices, where their homes are. So we do a little bit of filtering to try and get higher quality homes. Just because you have a high frequency of pings in one area doesn't mean you necessarily live there. We'll see people's work a lot of the time. So we try to do at least some filtering to get it, get a higher quality inferred residences. But the idea now, I'm going to move to this. The idea now is that we have, and we never, just to talk about the ethics of it briefly, we never interact or report individual devices. Everything is aggregated. We make sure that everything's, there's encrypted and least access user policies. So we try to at least take care of the data, and we're only really care about aggregate metrics derived from this. So the idea then is we have inferred residences. We can map those inferred residences to our tessellation, to our block groups. So each device then is associated with some block. So here I have the example going back to the previous graphic. In CBGC, there's 21, and in CBGB, 28. And over time, you can observe the movement of those devices. between different dwell clusters. So we don't really care about individual pings as much as dwell clusters. And the idea is we try to count or observe whether or not an interaction has occurred. And we have a loose definition of an interaction. The definition we used was, I think it's 2 dwell clusters within 100 meters of each other in the same hour. So we can tune that based on, but we wanted to get some responsiveness from this and not throw out too much of the data. And it seems like the reason we were kind of loose is we're not particularly concerned with we don't need to observe an interaction. We need the chance for interaction. And that's kind of what we're caring about here. So if we observe, just to clarify, what we do is we look at all the devices from C and all the devices at D, and we try to count the potential unique interaction, not unique interactions. I call it a device pair. If device A or if device 1 over here interacts with device 2 at any time during the course of a month, we call that a device pairing. And so we count those pairings over the course of a month, and we get a measure. We can normalize it over the potential number of pairings, which is the product of the number of devices. And that gives us a first stage estimate on the probability that devices from adjacent block groups interact. So just to kind of maybe show a little bit more on the calculation. So this is just, I introduced a new 1B. These colors are really not showing up. But between B and C, let's say there are 882 potential. Between B and D, I have 1,176. C and D, 588. And let's say, I can't even read this on the screen here, but I think 165 was the B to C. So let's say we just observe some number of device pairings, and we can just divide it by the potential, right? That'll give us these edge weights, which we then use in the final graph. So I want to stop and ask. That makes sense. Did that kind of make sense, or did I kind of jump through some things too quickly? Does anybody have any questions on? No. I'm sorry? How do we find a pairing? So based on the definition of the interaction, right, whether or not 2 dwell clusters are within 100 meters of each other within an hour time frame. So that's an interaction, right? And we can observe that in the data. The joins are horrible, but we can do it. And then for each unique pair of devices, like if I'm device 1 from C and back there's device 2 from block, from B, if our homes are associated with adjacent block groups, then we would count that as a device pairing. And even if we interact multiple times for this kind of first stage, we're not dealing with multiple interactions. We just care about if at any point over the course of 1 month, we observe a device pairing occurring. And so this simplifies a lot of calculations. It ends up being that what we can estimate is the probability that 2 devices, picked at random, 2 devices picked at random from adjacent block groups, one has to be from one has to be the other. What's the probability that they'll form a device pairing? And the reason this is a nice way to do it is because the calculation for 1 month works out like this. And then we can integrate multiple months of data, right? Communities are dynamic. People move in, move out, devices come online, they get shut off. So we have a lot of different time windows we can look at. And we use a naive Bayesian scheme. I mean, it's pretty simple. The math looks nice, right? But in the end of the day, it's a pretty simple calculation. And we can use that to update the probability over time. And it gives us a nice, I want to say convergence. But it helps us integrate those multiple time periods and account for those different, the community dynamics that might occur. Any more? Yeah.
This application people for stores in California.
Did you say for stores?
For depends on people.
Yeah. So let me talk. It got loud. in California, we had 600,000 devices in one period in like over the course of June. The goal of this is to kind of define geospatial communities that should be preserved, or maybe there's a good argument to keep them together for legislative representation. California in particular was an interesting case because California has really strong data protection laws. So it's the largest state in the country. There's 40 million people, and we had like 680,000 devices for, I think, June 20 or May 2020. I can't remember the dates. We went to Texas and Florida has around half as many people, and it had 1.5 million devices. So just on a side note, it's kind of cool to see the impact of data privacy laws that were pretty effective there. So I don't know if that helped answer your question.
It's only now this project is in California.
Good. No, that's a good question. No, we did it. We've been working on it in all the states because we have information for all the states, but it has to be done at a state level because communities, for this purpose can't cross state boundaries. There's a lot of, there's even reasons in the data that we wouldn't want to do it because things like the privacy protection laws, et cetera, et cetera. But we do have, I'll show a tool. We originally had work done for like 30 states, then we found a bug. But then we expanded and implemented the Bayesian scheme, and so we're working on filling out the map of the US. But right now I think we have California, Texas, Ohio, Alabama, and maybe one more. So I think was there a question back? Did you have a question?
No, you.
Okay, cool. So I'll just show, these ones are interesting. So we're in the process, both of these approaches, we're working on calibration, but the validation, it's very difficult to validate because of the issues that I talked about earlier. There's a lot of communities where we don't have information. Where we do have information, it's often conflicting. And in some places, where you might find a repository of communities of interest, which we have, there's a mix. There's like really good, well-defined, people put a lot of thought into it. And then there's like someone who started an idea and left it and abandoned it later on. So the validation is a little difficult. But this was a happy coincidence. The thing with the community detection algorithms that I didn't mention is we selected the lead-in algorithm, which was introduced in this, I can't say it's TRAG, T-R-A-A-G, I think it's 2019. It's a really fast algorithm that guarantees connectedness. And there's two parameters it takes. There's a randomness parameter, which is gets used to perturb the initial states. And then there's this resolution parameter. So higher resolution maps will have more communities. You're as a higher level resolution, you've got more little small pieces. At a lower resolution, you end up having fewer bigger communities. So I kind of arbitrarily chose to start with just a log scale. Let's go with 0.1, 0.001. This was done through, exploratory analysis, it's called that, on my computer. And so this is an example of what the Boyle Heights comparison looks like. So here's two of the public feedback from the 2020 period that I talked about earlier. So this was Elizabeth, this was Benjamin. Everything's public. So the information that I'm showing here, you could go find, no problem. It's all available on the CRC website. So this is what our community looks like. And maybe it's a little difficult to see on this, but here's the 710 freeway, and this is our eastern boundary. And right here's the 710 freeway, and here's Ben's eastern boundary. And here's the 710 freeway, and here's Elizabeth's eastern boundary. So that kind of generally matches up pretty well. One of the things we see is ours compares pretty favorably with Benjamin's interpretation, and there's a number of reasons why this could be. we have a little notch here that matches. The cemetery is carved out, and Ben thought that should be carved out as well. Elizabeth didn't. But also down here, there's this area called Commerce, California, and as a fairly standard rule of thumb in the U.S., if it's called Commerce, it's probably not a lot of people living there. It's usually like a big industrial. It's a generalization, but Commerce, California, there's not a lot of people. It's very industrial. Over here is kind of Vernon, and this is just a massive industrial area. So it's kind of hit or miss on how many, whether or not this would be included. And I can note that for this was generated using 5 months of data, and I think for 4 out of the 5 months we had no information in this area. So just to kind of point that out. But this is as a first stage validation, it's nice to see generally the same shape at least, right? Coming out of it. So maybe what I'll do quickly, I'll just show the tool for this one. If I can find it again. Do I have it up? Did it close? All right. Let's go to, I had it up and then it closed. So let me bring it up here. So this one's a little slower than the other one. And this one's actually live online, but it's very beta. And so it's not something that, we're sharing with stakeholders or there's a lot of exploratory analysis being done to kind of, so New Jersey was the other one I had. So let me pick Ohio. No, I'm not an expert on Ohio, but let's look at it. Takes a minute to load. The shape files in Shiny aren't great, and I'm not a Shiny programmer. Got the 3 dots. That's good news. Okay. So this one looks a little bit different. We don't have different dimensions of socioeconomic similarity that we care about. So for this one, for this tool, we have different levels that we can explore. So I'm just going to show like medium, large. And again, I'm not an expert at all on Ohio's communities, but I will say Ohio is a really, really contentious and interesting case in the United States. They've had their map struck down a couple times. They're one of the more notorious cases of kind of partisan gerrymandering, where one party's been able to embed themselves, in legislative power for the past, since 2010. And it looks like they'll be able to do it. But there's one of the things that occurs in the U.S. is, so I didn't really explain this, but state legislatures have the power to draw these maps. They can give that power to like a redistricting commission. So some states have done that with independent commissions. Usually the gerrymandering is associated with legislatures drawing it because there's incentive for me to draw districts that let me stay in power. So Ohio's one of those, but one of the things is there's lots of court challenges. So this year alone, Ohio's maps have gone through, like first they were approved by the state legislature, then they were struck down, then they were reapproved, then they were struck down again. They're on like their 3rd iteration. There's lots of court battles that go on. So these things can go on for years. And hopefully, we can help improve these, how these are drawn. But anyway, so going up and down the scale, you can see, all right, here's some medium large ones, and here's some large ones. And there's just different ways to slice and dice it. The tool has, again, the ability to look at the graph. So I'm going to just pick, again, this is clumsy programming. So like I can click one of these and it'll draw the graph for that particular one. Then I can change it and look at the graph. But there's some interesting things in here. You'll see areas where there are really tight, like dense, thick bars here indicating that we're observing a lot of device pairings between those adjacent areas. And then, areas like here where we don't really see much of anything. So you might see a community here, I'm just spitballing based on the way this looks. But yeah, I mean, it's kind of, I like exploring it. What else would I show on the tool here? You know, we do have overlays, and oh, this is what I wanted to show. Let me go back to this. So I forgot because we don't have this in the social one. Let me click on one of these here. Okay, we have this thing called intercommunity interactions too that we can look at. So if I click over here, one of the things you know that we have in the data is these device pairings can occur anywhere. So we may live next to each other, but we may commute to the same place, right? And we actually interact at work. And that's what helps define the strength of our community. So that's the idea behind this. And this graphic is supposed to convey, you know, I need a legend and some stuff. But the coloring on this is basically where the interactions are occurring, with where the device pairings are occurring that help us drive and define the edge weights on the graph. So, you know, looking at, I don't know, this is Northeast Cleveland. There's a community here. It looks like, based on the coloring, the red areas are denser. So, as far as communities outside of this one, where device pairings are occurring, it's occurring over here. And then it gets kind of less and less dense as you go farther out. So the idea is to think about, you know, between communities, what's the strength of connection? Or like, do we have a qualitative way to kind of evaluate that? So we have these graphics for this. I think they're kind of cool to look through. And the hope would be, not only can we help identify where these communities are, but we can think about which communities might have ties to each other and be worth keeping, and which ones may not have ties to each other. So I think I'm starting to run up on time. So let me go back here. I apologize. This is a new experience for me doing the not mirror screen slideshow, and now I have to scroll back. Okay. So really quickly, I'll just give. I'm gonna drive through this quickly. We are working on calibration and validation. There are some metrics that were developed or talked about recently in the redistricting literature. So there's this effective splits index and this uncertainty bits. These are two measures where you're trying to measure how much a community is split. And so our idea is to take the COIs we've generated, compare them to you know, a pool of empirical data that we have. There's this project called Representable, and so they collect COIs from people who want to provide it. As an example, I think California has 60 COIs. They're not extensive, but it gives us at least something to look at. So we want to overlay ours versus those, and then calculate these metrics to see like how much do our maps split up those communities. So this is going to be imperfect because there's a lot of variation, and again, communities that are defined there might have, you know, a lot of uncertainty. But we want to at least try and get something. Yeah, I mean, the uncertainty bits is basically the Shannon entropy for when you look at the splits across it, and then I can't remember exactly how the effective splits is calculated, but they're pretty straightforward things to calculate. One of the other pieces that I'm hoping to do here is a comparative analysis across them. So with the socioeconomic data, we're going to get a whole bunch of edge weights, right? And then with the geolocation data, we have a bunch of edge weights. So I think it's going to be really interesting to explore the relationships between those two. Maybe try and understand which socioeconomic factors best explain colocation. I think this could be really interesting to use these to answer other questions about, you know, diversity and integration. Do people spend their day following around people that they look like, or are there other factors at play? I mean, I don't know. So hoping to use that information here in the next couple months to explore some of these questions. Let me skip to this. You know, one of the things I will include are implications, recommendations for policymakers. That's important because we all work in policy. And I think big data. Again, there's data for good, there's data for bad. It's technology, and there will be people who misuse it, right? and just the way people misuse it right now in the redistricting process. So how can we protect against that? I want to have a discussion about that in the dissertation. But final piece here is it appears as though, and I haven't had time to investigate Mexico's kind of census data since I was here in late March, unfortunately. But it seems like this could be implemented in Mexico if one were interested in doing that. I think there's data on indigenous populations, on language, on income, and it's all associated with. I think someone knows what these are called, what the levels of these are called. What are they? Ahips. Okay, I'm saying it wrong. But anyway, so there is this information, and this is a tessellation. I mean, it's the same thing, right? There's a tessellation of. I mean, I'm looking at Mexico City, but you could feasibly apply this here. Now, I'm not advocating one way or another, and I'm not saying cell data or socioeconomic data is wrong, but I do think there are implications for thinking about this in other democratic states where we care about representation. So I had put up, some of the questions. What are the potential applications? But I don't know. I think now it's just time to cut. I think I got them 5 minutes early. Yeah. Are there any? I think I can answer some questions, right? Is that legal for like 5 minutes? Okay.
Hacemos un par de preguntas. Ya bien total el tiempo que necesitamos para que podamos poder tener tiempo para la sesión de networking y temas. Entonces, no sé, pero es más importante.
Is there a way for the model to account for time dynamics? I mean, and we'll say this means something change in.
So yeah, like with the geospatial, or I'm sorry, with the geomobility data. I mean, the communities actually. I don't want to say they changed drastically, but we do it on month-long periods, right? So we have dwell clusters for devices for that month, and we kind of treat them separately. So one of the things that was interesting is we had a great econometric setup. We had data right before the pandemic, data right at the pandemic, data right after. So you could see this like massive drop-off in movement. The communities really shifted, and the edge weights changed. So the geomobility data is a little bit easier to use for that. Now, I wouldn't advocate, the reason we take the Bayesian approach is because we want some stability. We draw districts, this is just how we do it, I'm not saying this right. We draw districts for 10 years in the US, right? And obviously lots of changes happen. By the time, they have to have rigorous population standards at the beginning. By the end of the 10 years, I mean, some of the variation can be like plus or minus 10% within a state. As people move, lots of things happen. But you have to try to draw communities that are stable at the time. So that's why we use the Bayesian approach. Now, if you wanted to, observe how those communities change over the course of a year, you can absolutely do that. I mean, it's just selecting those communities. The census data is a little bit more difficult. The ACS-5 is updated every 5 years, so you can do that. But those are estimates, and by the end of 10 years, they're actually pretty far off sometimes. But absolutely, you can incorporate time dynamics. Okay.
Is that correlated with any social variables that state? Does that complicate this or does that not?
So we did do some analysis on that. By and large, it actually turned out to be pretty okay, but there was a slight kind of bias towards wealthier people. The one that was more important was age. So, generally, you miss a lot of older individuals who may not have cellular devices, or if they do, they're not like on apps. There's just kind of an age distinction that stuck out pretty well. But we did, there was something we observed in the data. with respect to income and age. And then I think there was this, I don't think we actually saw any differences across. So we weren't able to actually associate the devices with the owner, right? To say, because we don't have that data. So what we did is we compared it to census data, where our inferred residences were, and then tried to look at, do we have more residences associated with certain areas than others? It's a good question, and it's something that we have to talk about. I think we didn't do a rigorous statistical analysis on it to generate some power on it. But yes, those biases are in there, and they should be probably considered, especially because these are legal boundaries that we're talking about. So I wish I had a stronger answer for you or a longer one. But we did see those. Yeah?
Y los queremos invitar el siguiente miércoles. Vamos a tener otro evento acá. Va a dar una conferencia al decano sobre transformación pública en tiempos de populismo y unos talleres como de cada uno de nuestros programas de maestría. Y así está el QR en las pantallas.